All right, let's work through these problems here together. Example 1 says Benjamin watches a thunderstorm from his apartment window, sees a flash of lightning bolt, and begins counting seconds until he hears the clap of thunder 10 seconds later. Assume that the speed of sound in air is 340 meters per second. How far away was the lightning bolt in meters and kilometers? Note speed of light is 3 times 10 to the 8th, considerably faster than the speed of sound, which is why you see the lightning so much sooner than you hear the thunder. So we're going to just say that that pretty much is instantaneous, that you're going to see that. They do occur pretty much simultaneously. We just don't hear the thunder for a long time. All right, so let's take a look at what we are given. And this is, I think, the important thing. And you need to get used to doing this all the time in physics. You need to write down your given. So in this, I have the velocity, 340 meters per second. We know that's the speed of sound. I know that it's 10 seconds. What am I trying to find? That's what I'm trying to find. I'm trying to find the distance. And my equation is change in distance over change in time, or change in displacement over time, to give me a velocity term. Well, all right, so that's pretty simple. If we plug in the things that we know 340 meters per second for our velocity. We don't know the distance, and we know 10 seconds for the time. So if we solve for D, we're going to get 3,400. And if I multiplied that, I mean, my seconds are going to actually cancel out. And so I'm going to get 3,400 meters. And then if I want to convert that to kilometers, I'm going to divide by 1,000. Or I could think of, hey, well, we've got 1,000 meters, 1 kilometer. That's going to equal 3.4 kilometers. All right, let's go to number 2. On May 29, 2005, Danica Patrick was named the first female Indy 500 Rookie of the Year after a 4th place finish. Best Indy 500 finish of any woman in the event's history. She completed the race in time of 3.174 hours. What was Danica's average speed during the 500-mile race? Note, generally the unit miles is not used in physics exercises. However, the Indianapolis 500 is a race that is measured in miles, so we're going to use miles here. So let's take a look once again. And guys, I want you to do this, even on the problems that you're doing, just for practice, even the ones you're doing in class. I want you to write down, what are you given? If you don't learn to do this, you won't do it on the test, and you won't get them right. So write down, you're given D equals distance 500 miles, time 3.174 hours. And we want to figure out, or we don't know the average velocity, okay? So we want to figure out what that's going to be. We know that velocity is distance divided by time, okay? So let's figure that out. Velocity equals distance divided by time equals 500 miles divided by 3.174 hours. If I calculate that out, it comes out to be 157.5 miles per hour, mi per h. 157 was her average speed. That's pretty fast. It's not bad. All right, number 3, the slowest animal ever discovered was a crab found in the Red Sea. It traveled with an average speed of 5.70 kilometers per year. How long would it take this crab to travel 100 kilometers? So write down what you're given. Here's what I'm given. I know distance is 100 kilometers, velocity 5.7 kilometers per year. And then also write down, what are you trying to find? Well, we're trying to find time. There's my formula. Time is distance divided by velocity. Or I like to just remember velocity equals distance divided by time, and then I solve for the one that I need to. In this case, I do need to solve for t, so I'm going to get t equals d over v. But I would prefer to remember it one way, not the variations that go with it. It's just easier, at least for me anyway. So plugging in, well, 100 kilometers, 5.70 kilometers per year. So if we take 100 divided by 5.70, we're going to get 17.5 years. So for this crab to go 100 kilometers would take it 17 years. Pretty slow. Not sure how something like that ever finds anything to eat. All right, example 4. Tiffany, who is opening in a new Broadway show, has some limo trouble in the city. With only 8 minutes until curtain time, she hails a cab, and they speed off to the theater down a 1,000-mile long one-way street at a speed of 25 meters per second. At the end of the street, the cab driver waits at a traffic light for 1.5 minutes, then turns north onto a 1,700-meter long traffic-filled avenue on which he's able to travel at a speed of only 10 meters per second. Finally, this brings them to the theater. Does Tiffany arrive before the theater lights dim and draw a distance versus time graph of the situation? So in other words, how long does this take her? So what do we know? Well, we know that the distance is 1,000 meters. We know that the average velocity on the first segment, I think I cut off part of this, so we'll just put the rest of that up there as we go along. But 1,000 meters, she was traveling at the rate of 25 meters per second. So if we're back to velocity equals distance divided by time, and we know velocity, and we know distance, and we want to solve for time, it's going to be distance over velocity. So time is going to equal distance over velocity. So 1,000 meters, 25 meters per second. And so that's going to take her 40 seconds to cover that first part. That's the one-way street. Okay, so then she stops at the stoplight for 1.5 minutes. 1.5 minutes, or what would that be, 90 seconds. Okay. And then the third part, she is traveling down the other street. The distance is 1,700 meters. The average velocity is 10 meters per second. And once again, I'm trying to find time. So here's my formula again. Same thing. So distance divided by velocity, 1,700 meters divided by 10 meters per second would be 170 seconds. So if we add all those up, that comes out to be 300 seconds or 5 minutes. So, yep, she made it in time. She's even got 3 minutes to spare. Okay, so then the second part says draw a distance versus time graph of this example. So if we look at that, distance versus time graph, notice how, okay, this first part, pretty steep slope. That's the fastest that she went. Then she got stuck in traffic, or got stuck at the stoplight. So she didn't move anywhere. So the time kept going, but the distance didn't. And then she got moving, but not quite as fast. So notice the slope of this first line, not quite as steep as the slope of the second line. And that's what it should look like. Okay. All right, example number 5. Grace is driving her sports car at 30 meters per second when a ball rolls out into the street in front of her. Grace slams on the brakes and comes to a stop in 3 seconds. What is the acceleration of Grace's car? So let's put down what we have. And some of this is a little bit different than what we had out of the notes, but we're talking about VO. VO stands for initial velocity. So her initial velocity is 30 meters per second. V0. V sub 0 is what that's supposed to mean. VF, final velocity, was 0. She comes to a stop. So she goes from 30, she's going 30 meters per second, slams on the brake, down to 0, does that in 3 seconds. And we want to figure out the acceleration of that particular equation. So let's go back and let's talk about acceleration. First of all, acceleration is the change in velocity over the time. So we want to know, what is the change in velocity? In other words, you go from, a lot of times they'll write change in velocity as being final velocity minus initial velocity over time. So what's the final velocity? Well, that was 0. So 0 minus the initial velocity of 30 meters per second, and the time was 3 seconds. So what we're going to get is negative 30 divided by 3, and so her rate of acceleration would be negative 10 meters per second. Now, when they're talking about 10, the negative number means that she's slowing down because we're talking about it's opposite of the direction of her velocity. So that would be a negative number. Now, the other option, if you hadn't done it with that, you would have to have said, instead of getting a negative 10 meters per second, you might have gotten 10 if you just said, oh, that's 30. I've changed 30 and divided by 3, I get 10. But you would know that the acceleration is opposite the direction she was going. So sometimes you can reason some of that out too. But that's the reason why this one is negative. All right, I think you are ready to go ahead and try those sample problems in class. So we'll let you give that a shot.